This is the last talk in the programming models track, and I thought it would be good to sort of lower the level to a very simple programming model, which we call asynchronous dynamic load balancing, and a piece of software called ADLB that implements it. And I guess we could start by drawing a distinction of two very general approaches to parallel algorithms. Of course, there are variations on these and combinations and so forth. But I think of data parallelism as the kind where we're doing the parallelism on a grid. We're using parallelism from the fact that physics is very local, so we have patches that operate in parallel with communication going between the patches, and sometimes global collective operations. And in many of these cases, not all cases, but in some cases, the same amount of communication is done in at each step, and so load balancing is not so important. Sometimes it's very important, but many times it isn't. Task parallelism, at least at the very highest level, there are different kinds of task parallelism. The work that's to be done consists of largely independent tasks, and that's the source of the parallelism. The tasks may not be of the same type. They might take very widely differing times. We assume that there is not too much communication between the tasks, and the dependencies among the tasks, it's not just a single bag of tasks, there are dependencies among them, that has to be managed, whether it's statically or dynamically in some way. But load balancing is fundamental. So just to get the terms right, what I mean by load balancing is the assignment of tasks, and I think of a task or a work unit, different systems use different terminologies, to processes so as to minimize the amount of time that processes are idle. And static load balancing means that you can work this all out ahead of time, who's going to do what when, and some algorithms work well that way. Or dynamic load balancing, which is often, especially in the early days, was done by a master process which coordinates the starting and stopping of the work units. And that requires communication between the manager process and the workers, but tasks may create new tasks, so you have new problems popping up, and the tasks might be quite different from each other. So many people's first parallel program, certainly mine, might have looked something like this. There's an easy way to get good dynamic load balancing if your algorithm can be expressed this way, where there's a manager who keeps track of the work units, and you have workers which talk to the manager, putting things in the work pool when there's new work to do, taking things out. When a worker is finished, he tells the manager that he's finished. The manager gives him a new piece of work. So it's very easy to do that in MPI with these put and get operations, are just communication, send and receive communications between the worker and the workers and the manager. And it solves some problems. This implements a very simple but effective form of dynamic load balancing. The manager can manage the termination problem. Tasks can be created dynamically because workers can, as the result of completing one task, tell the manager to put some more new tasks in the work queue. Oh, and when I say work queue, I don't mean queue strictly in the computer science terminology. I just mean a data structure that holds things that have to be done. But this provides some scalability problems when you have lots and lots of workers. So this doesn't work so well. In two ways, the manager can become a communication bottleneck. That sort of depends on how big the work units are, but if there are lots of workers and the tasks are small, then you can see how the manager would be a communication with the manager would become a bottleneck. And also, if we assume here that the manager is the one who keeps track of all the work, if there are lots of work units and maybe the description of a work unit is a large thing, then you're making the one manager handle all the memory, and that gives another type of bottleneck. So the idea behind ADLB is to try to recapture this very simple model, but in a scalable way. So we'll describe a task as being just a string of bytes. So the application defines a thing, for the ADLB library. The ADLB doesn't know anything about particular tasks. There's not going to be an explicit master for load balancing. Rather, workers are going to make these same types of put and get calls to the ADLB library. And there might be some MPI communication going on inside there, but the application doesn't know about it. And we'll have a very simple put and get interface, basically this sort of the same one we had with the original master worker thing. And it goes into a distributed, those operations interact with a distributed work queue, and that hides the MPI calls. And we can move things around inside the distributed work queue in the background. That's what makes it asynchronous. So we've sort of turned the picture upside down like this. There is a shared work queue. The workers do pretty much the same thing they did before. They get a task, they do it, they tell the work queue that it's done. They can put new things in the work queue, so it doesn't really change that. This is not really a new idea. The old programming library, Linda, did something very much like this. But the new thing is that we need a scalable, portable, and distributed implementation of that shared work queue, and there can be quite a bit of complexity hiding inside this very simple interface. So the interface is simple in this sense. Here's the complete API, and it really only has, the only important part is the put and the get. So there's a single put. You can put in a work of a certain type. It's described by a buffer address and a length. It has a priority. If you want to, you can specify that only a specific process can do that work, and you can specify where the answer that comes out of that computation is to be reported. The get is in two steps because you want to ask for work, but before you actually get it, you need to know how big it is. So you reserve it, you get back how big it is and a handle, and then you get that handle and you supply the buffer that the work unit description is going to go into. And the rest of it is just a little bit of optimization and housekeeping. There's an init and a finalize like there is in MPI. The fact that you have these extra arguments like the types and the rank to report answers to and the target rank can be used to implement several different kinds of algorithms. So it's not, in some ways it's not as simple as it looks. That is, the simple interface can be used to implement fairly sophisticated patterns, and we do that in the application that really started this. If we default on those, we let those parameters default, we have a very simple, high-level work stealing type of API, and we'll look at some examples. If you use the fancy ones, then you can allow more elaborate algorithmic structures to be expressed. And that allows ADLB to be used as an execution engine for higher-level models. So there's a Swift parallel workflow management system that uses ADLB under the covers as its execution engine. So we have experimented with a number of implementations of this. One advantage of having a very small API is it's not such a big deal to change the implementation in fundamental ways. But rather than report on all of those, let me just tell you what we do in the current production implementation that you can download. I'll tell you about that later. You divide the processes up into application processes and ADLB servers. Very simple idea here. We statically attach the applications to specific servers. So the put-get operations happen between an application process and its server. And then the servers themselves communicate a lot between each other in order to keep up to date the status of the shared work queue. So the work is now, the units are spread around among the servers, and it might happen that you ask for a piece of work that's available in the system, but it's not on your server. So the server has to know where that work unit can be found and fetch it for you. So to make this work, I thought it would be worth noting that to make this work, ADLB uses lots of MPI features beyond the simple ones. So it uses the fact that there can be multiple communicators because it divides the application message passing space from the server application space. The servers use the non-blocking probe so that they can be extremely responsive to requests. MPI data types are used for for the description of the work pool that gets circulated among the servers. Servers use all non-blocking sends and receives, and they keep a queue of MPI statuses that record whether those are finished or not. And every time it goes through the iProbe loop, it does a test on all the things in that queue, which kicks them all along, and it never ever has to do a wait. So you don't really have to wait on a non-blocking send or receive. You can just keep testing it until it says that it returns a status of complete. The client side, that is the application side, uses the MPI synchronous send. Remember, that holds it until the receive has been posted on the other side. That saves memory overload in the server so that it doesn't get anything new until there's room for it. And we mentioned the other day how the ready send can be used to respond to queries, and we take advantage of that in ADLB. And MPI provides the portability for this, so this can be run on your laptop or on Linux clusters, or anywhere you can run MPI, you can run ADLB. And we use the profiling library to understand behavior. A typical application looks something like this. There's an MPI in it, there's an ADLB in it, and on the ADLB in it, you say how many servers you want. Different applications find that they need different proportion of their MPI processes to be dedicated to ADLB servers. It depends a lot on the granularity and the size of the work. So sometimes you can get by with only one server. Sometimes you need, say, 10% of your application, of your MPI processes should be servers. So when you call that, you'd get back a flag that says whether you should be a server or not. And if you're a server, you call the server routine, and now you're executing the ADLB code. And if you're not a server, then this is where the normal application code goes. So it's pretty easy to convert something into an ADLB program by just embedding that code in this spot. Let's look at 4 examples. One just for fun. I told you this would be a lightweight talk. And look at a couple of other applications, including the serious application is the one that motivated the development of ADLB to begin with. So does everybody know how to do Sudoku? Pretty much. So the idea is that you get a puzzle like this printed in the paper every morning, and what you're supposed to do is fill in a number from 1 to 9 in each box so that the numbers 1 to 9 occur in each row and in each column and in each one of these 3x3 boxes. So I'm going to show you an algorithm for doing this with ADLB, which is not a really good algorithm. You should use math to do this. But it fits on one slide, so it makes a good example. So here's the whole program. So the way it works is that a single process reads the newspaper and does an ADLB put of the puzzle. So the work unit, that is the task, will be a partially completed board like this. So you start with the one in the paper, you put it in the pool, and then all the processes execute this loop here. So they all get a board, that's the reserve and get, and then while they've gotten one, I mean, if they couldn't get one, then you're done. We'll see how that's handled in a second. You find the first blank square. If there isn't one, then you're done because you've filled things in altogether. Otherwise, you just look up and down and around your box to see what possible values could go in there using a very simple algorithm, not anything fancy. And then you set the blank square that you're looking at to that value and put a new board back in the pool. So sometimes you're putting multiple boards in, sometimes you're not putting anything in. So it looks sort of like this. Here's the pool of work units. There's a single put at the beginning, and then everybody does this in a loop until you're done. So he looked at the first blank square. He saw it was possible to be either a 4 or a 6 or an 8. So he makes all 3 of these and puts them back in the work pool. And so you just run this until you're done. So there are, you can combine some smarter strategies in here if you wanted to. This OOH here, that stands for optional optimization here. So after you've gotten a square, you could put in, you could do some other fancier stuff to see if you could eliminate some of the possibilities. So even if you did that, you will find that there are a lot of work units generated this way. And you can use things like priorities to solve this. So that's something built into the ADLB system that can be used in different ways by different applications. What we might do is, when we did the put, that's when we assign priorities, we'll make that the priority to the number of filled squares. So that means that the more complete the board is, the more likely it is to be assigned to someone next. So that gives you a sort of a depth-first search for the solution, which might be the way that you would do it by hand or sequentially. ADLB will figure out when the pool is empty. So you might want to prove to yourself that there's only one solution to this problem, or there's no solution. So that's Sudoku and ADLB. I just mentioned this application from some guys I know over in our physics division. So they work on material science. They do a parameter sweep to try to find for properties of a certain material. And what the physics is not too important. What was kind of interesting is that they had a sequential program that looped through lots of different configurations that had the different configurations took different amounts of time to compute. But they parallelized it by using ADLB, and they never learned any other parallelism system at all. They didn't learn MPI or OpenMP. They just used the very small number of functions in ADLB, and it made a big difference to them. A friend of mine is an administrator for a cluster where people submit various kinds of sequential jobs, and he needed to distribute them around the cluster. And so made it this very simple batch scheduler. You just read a file of command lines, put each command line in the work pool, let ADLB pull those out and execute them with the Linux system command. Very, very simple, but solved its problem. The original problem was a nuclear theory problem. The Green's function Monte Carlo calculation that's done has been done at Argonne for a long time. This is the gold standard for accuracy in simulating the behavior of small nuclei. So this is an old code. As a parallel code, it's an old code. It has always had a fairly non-trivial manager worker algorithm to do various pieces in this Monte Carlo calculation with different work types and priorities and so forth. And he had it scaled to about 2,000 processes and then hit a scalability wall due to load balancing issues. And we wanted to get to at least 10,000 processors in order to calculate calculations on carbon-12. And the algorithm threatened to get hairier and hairier with more types and dependencies among the work units and difficult load balancing. So we actually, but we wanted to maintain that original manager worker structure of the code, and that's what sort of got us thinking about something along the lines of ADLB, and that ended up simplifying his code greatly. But now it runs with hundreds of thousands of processes. To make it scalable was a kind of a multi-step process. It wasn't quite as straightforward as I may have led you to believe that it could be. Balancing the processing wasn't so difficult. That's sort of automatic in the manager worker work pool scheme. But then we needed to do balancing at the memory level and then eventually load balancing at the communication level. It seems to be working pretty well. You can get it if you like at this website. My partner Ralph Butler at the University of Middle Tennessee State keeps the repository. And so if there's a download button at that website, and that will give you the source and the configure script that'll build it on your machine. All the examples I've been talking about, including an example of doing the well-known traveling salesman problem, which can also be branch and bound searches also work well with ADLB. There have been some recent developments that have come from the fact that my physics friend now wants to do bigger nuclei, and that makes the work units bigger, and that means that he needs more memory to store the work units. That means he needs more servers, because that's where the work units are stored. And the more servers he has, the fewer computing client processes he has. So that was somewhat of a bind. So we thought about trying to build something into ADLB, but it's actually complicated enough. It has a simple API, but it's pretty complicated under the surface. So we used an orthogonal approach. We did another very small API library, which we call DMEM, and it's just a way for an application process to give a chunk of memory to the system, let the system, the whole distributed system, find some place to put it where there is room for it, and it returns back a handle, which is a very small thing, that essentially says where it is and where it is on that process. And DMEM manages memory on all the clients, running as a separate thread in each application process. So now we have lots and lots of memory servers. They communicate with MPI. And then ADLB only has to deal with these handles instead of all the work units, because the handles are small. So it doesn't need so many servers. Now the memory for the work units is spread around all over everyone. And this works pretty well. And the object size for DMEM is an 8-byte integer, because we think things are going to get bigger. So the the DMEM API is like this. There's a put, a get, copy, get pieces, update pieces. Doesn't amount to much. That's the main point. And there is also a Fortran API and so forth. This is all implemented, and you can get it from the same place as MPI. It's not connected to ADLB in any way. ADLB uses this library. So I want to talk about, I think I've discovered a general concept here called the LFP. The LFP is a lurking future problem. So you don't have that problem yet, but you can sense that you're going to. So machines of the near future are going to have lots of memory. So this will mean we'll use them for very large work units. We'll have lots of threads to work on those huge work units. But what if ADLB or even DMEM application wants to use work units that are larger than 2 gigabytes in size? Now, 2 gigabytes is pretty big for a problem description, but we can see this coming. ADLB and DMEM are both completely agnostic about what's in work units, so they send messages with data type MPI byte. And the MPI send and receive, as you recall, has an integer as the count argument of data types. So with the MPI API, you cannot trivially send a message of longer than 2 gigabytes in length, because the length is specified by an integer. An integer is still 4 bytes on most systems. So the MPI forum debated it a lot, different ways to fix this, and decided not to. See, the choice was to change the signature of the MPI send and receive and various other functions from int to aint, or they ended up using something like MPI count that would handle long integers. Well, you don't really want to change the MPI API. Or you could add a new copy of each function. I think there would be about 50 more functions that way, which would just be the same as the ones that everyone knows, except for this one argument. So they decided that you can really get around this by using MPI data types. So the count is a number of data types, So you can bundle your bytes into big chunks, and then your count argument can be smaller. So they decided, well, this is really a solved problem. But there are two problems. One is a convenience problem. Some people don't like to build custom data types. They would rather just send a long message. And I discovered, somewhat to my dismay, that on several machines, the underlying communication mechanism won't handle something longer than a gigabyte. So you can describe it nicely, I mean in 2 gigabytes. So you can describe it nicely in the MPI send, but the underlying system will truncate it, or it will crash, or it will do something strange. So in that case, you need to break your message down into several messages and send them, introducing another level of complexity. So the solution is another small library, which we call MPIL for long messages, and it just has some number, not yet decided how big it will get, of functions that look pretty much like normal MPI functions, but there's a MPI count argument which is big enough. So the implementation just started doing this a little while ago. It's not quite done yet. And the idea is that you would use this library for sending long messages. It'll also deal with short messages, of course. And if the machine will send in one message a long string of bytes, then it does it in a single, then it constructs the data type, you don't have to do it, and sends it in one message. And if that won't work, then it automatically switches to dividing up the message and sending it in pieces, and one has to, that introduces a level of complexity, but that'll all be hidden from the user. ADLB gives up some generality. You don't want to do everything with this master worker thing, but if you give up generality, you might be able to get quite a lot out of a very, very simple interface, and I like simplicity. GFMC was what motivated ADLB, and that motivated DMEM, and that motivated MPIL, but those are all still separately independent libraries that can be used generally if that's the sort of thing that you need. DMEM was a big help to making ADLB scale to larger work units, but it's also generally helpful. MPIL, when it gets finished, will be a simple way to provide long message support on all machines. And my real message is that even little bitty libraries with between 6 and 10 functions in their API can be useful.
Well, I was curious, this sounds interesting, but you say you have a system where you have some large memory nodes that could serve well as the servers and a whole bunch of less smaller. Can you set it up such that you can specify specifically which servers are used as the servers?
Yes, we do that not for different sizes, but really to spread the servers out among the nodes. So yes, there's a way to do that. For DMEM, there isn't a way to do that right now, but there is a single little function that decides if there's not room locally to do this, we try to make all those puts locally if we can, then call this function to decide where it should go. And currently it has a number of different algorithms. Always go to the next guy, choose someone at random, figure out who likely has the most memory left, send it to him. So there's just a bunch of little cases, and that case could be added in probably 10 lines of code.
How do you encode dependencies among the tasks?
Well, so there isn't an explicit task graph, which is the case, which there is in some task-based systems. Rather, it's what the workers do. So if a task is not ready to be executed, you don't put it in the pool. So there might be some communication among the workers that take to know the different pieces. So for example, let's suppose there's a task which wants to divide up its work into various other tasks and have those worked. So what it might do is divide it up, put those in and wait for responses, wait for the answers for all of them, so that it can then build the next step of the unit. So the task dependency graph never appears anywhere, but you can implement a quite complex one that way.
Is algorithm coordinated work of the
Servers?
supervisors of scheduling units? Is that like a new algorithm or standard algorithm?
No. So there isn't a scheduler. There's no process that does scheduling. There's this pool of work. Okay, so what happens is you ask...
Over multiple nodes, right?
Yes, they're stored, spread around somewhere, they move, but we know where they are. So process finishes what it was doing, saying, I would like next to work on a work unit of type 15. So he sends that to his server. Of course, it might have disappeared by the time it gets there, so there are some race conditions to be dealt with. But the basic idea is if the work unit is there somewhere of that type, then the guy will get it. And you can avoid stalling if you want to ask first whether there is work available of a certain type, and if not, ask for something else. In fact, when you ask for work, you give it a list of types, and it'll try to find one of these, and if not one of these, and if not one of these.